Welcome to this session. In this session, we are going to discuss about the last property on Laplace transforms, what we call the final value theorem. So I'll give the statement and then do an example to see how it's applied. So let's see. So one thing to note is that for us to apply this theorem, then S must be real value for the function f of S. So the final theorem states that limit as S approaches 0 of S times f of S is the same as limit as S as t approaches infinity of f of t. So things to note on this theorem. One, the theorem applies only to real values that this theorem is only applicable for real values of S and for functions f of t which have limit as t approaches infinity. And then another thing to note, care is needed when applying this theorem. So since the Laplace transform of some functions exists only for real values of S greater than 0, so we need to be careful when applying this theorem. Since the Laplace transform for some functions exists only for real values of S which are greater than 0. So in that case, taking limit as S approaches 0 is sensible, is not making sense since the values of the real values of S are those values which are strictly greater than 0. So let's illustrate how to apply this theorem on a problem. So example. verify the final. Verify the final value theorem for function f of t equals to e raised power minus 2t. So we'll be required to find the Laplace transform of this function first. So solution. First thing is to find capital F of s. So Laplace transform of e raised power minus 2 will be the integral from 0 to infinity e raised power minus st e raised power minus 2t dt, provided that real part of s is greater than negative 2. So this s must be greater than negative 2. So this is the same as integral from 0 to infinity e raised power. Now I can factor out negative, then I say s plus 2 t dt. These are very easy integral to evaluate. So integral of e raised power minus s plus 2 t dt will let u to be minus s plus 2 t. So which means the u is negative s plus 2 dt, which means dt is equals to negative du over s plus 2. So which means this will be integral of e raised power, this one here, e raised power u times negative du over s plus 2. So this is the same thing as writing negative 1 over s plus 2 integral of e raised power u du. So which is the same thing as negative e raised power u over s plus 2. So then now to evaluate integral from 0 to infinity e raised power negative s plus 2 t dt will be, so we'll have a negative e raised power s plus 2 t s plus 2, 0 to infinity. Now do the same thing as writing 1 over minus 1 over s plus 2 into 1 over e raised power s plus 2 t 0 to infinity. Remember, these are limits for t. So when t is infinity, infinity times this s plus 2 is also infinity. E raised power infinity is a very large positive number. So 1 over a very large positive number is approximately 0. We'll have negative 1 over s plus 2 into 0 minus. Now when you replace 0 for t, so e raised power 0 is 1, 1 over 1 is 1. So which will give us negative, negative is positive, so 1 over s plus 2. So therefore, capital F of s is 1 over s plus 2. And this applies whenever s is greater than negative 2. But this thing must be greater than 0. So since we only require this to be greater than -2, it is permissible to let S approach 0. Now limit as S approaches 0 of S times capital F of S will be limit as S approaches 0 of S, F of S is 1 over S plus 2, which will be by direct substitution 0 over 0 plus 2, which is 0 over 2, which is 0. Also, limit as t approaches infinity of f of t is limit as t approaches infinity of e raised to power -2t, which is the same as limit as t approaches infinity of 1 over e raised to power 2t. And clearly, when t approaches infinity, 2 times infinity is a very big number. E raised to power a very big number is also a very big number. So 1 over a very, very big number is approximately 0. So limit as S approaches 0 of S times capital F of S is the same as limit as t approaches infinity of f of t, and the theorem final value theorem is verified. So that's how we apply the value theorem, or the final value property for Laplace transforms. Thank you.